Assalamualaikum and hi everyone. So we are from grade 6. We'll be presenting the group project which is the problem solving case. So the problem solving case that we choose is knapsack problem. Before we start, let me introduce you our teammates. So firstly we have me, Asyraaf Danial 284368, MAZUQI ADHA 285215, Muhammad HADIF 287852, and lastly AHMAD AZEEM with metric number 288777. What is knapsack problem? The knapsack problem is a fundamental and widely studied optimization problem in computer science, operation research, and mathematics. It belongs to the class of combinatorial optimization problem, where the goal is to find the best combination of items from a given set subject to certain constraints. So why did we choose the knapsack problem as our problem solving case? This is because we have chosen the knapsack problem for its practical relevance and its ability to represent real-world scenarios in a straightforward yet challenging manner. The problem's conceptual settings is relatable and can be visualized in various everyday situations, making it an excellent choice for introducing optimization and algorithm design concept. So for the scenarios of the knapsack problem, imagine you are a hiker preparing for a challenging journey into the wilderness. You have a limited carrying capacity represented by knapsack, and you are faced with a set of valuable items, each with its own weight and value. Your objective is to decide which items to take with you, maximizing the total value of the items while ensuring the combined weight does not exceed the knapsack capacity. Formally, the knapsack problem can define as follows. Given a set of n items, each characterized by a weight Wi and a value of Vi, and then a knapsack with a maximum capacity W. And to find the subset of items to include in the knapsack that maximizes the total value, while the sum of their weights remain within the knapsack capacity. Over the years, numerous algorithmic approaches have been developed to solve the knapsack problem efficiently. So in this case, we choose a brute force as one of the simplest methods, explore all the possible item combination, while the next one we choose the dynamic programming. It is a more sophisticated technique, optimizes the solution by breaking the problem into the smallest sub-problems.
So hi everyone, in this part I'm going to share with you guys about a little explanation about comparison between brute force approach and dynamic programming approach in solving knapsack problems. So the first thing is part is the brute force method. So the brute force method checks all potential item combinations that have been listed and computes all the total value for each combinations. So in the context of a knapsack problem, the brute force strategy is systematically trying out all potential combinations of items. It used to determine the optimal subset that optimizes total value while preserving within the knapsack's capacity. So the second one is the dynamic programming. So dynamic programming defined as a strategy for addressing issues with overlapping subproblems. In the context of the knapsack problem, dynamic programming divides the problem into smaller subproblems and performs memorization or tabulation. So it used to determine the optimal arrangement of items with the highest value while maintaining the knapsack's capacity. So moving on to the next one is the algorithm demonstration. So I'm gonna explain with you guys the algorithm demonstration for these two techniques, which is the brute force algorithm and the dynamic programming algorithm. So begin with the brute force algorithm. So the brute force algorithm works like by listing all the possible combinations of items. Second is to evaluate each combination. Third is to find the optimal solution. Then the last step is to repeat step 3 for all potential combinations that have been listed until you discover the one with the highest value that meets the weight requirement. So the weight requirement means is the knapsack capacity, the maximum value of the knapsack capacity. So here's an example question that involving the knapsack problem by using the brute force approach as a solving method. So in the table stated above, in the table consists of 4 items that have been named the item number 1, number 2, number 3, and number 4 along with their weights and their values. So like item number 1 consists of weight equals to 2, value equals to 12. Item number 2, weight equals to 1, value equals to 10. Item number 3, weight equals to 3, value equals to 20. And the last item, which is item number 4, weight consists of weight equals to 2, value equals to 15. So the knapsack capacity equals to 5, which is the max value. So the first thing first is each item will be represented by a number and the binary representation, which is the 0101, used to indicate whether an item is included as 1 or not included as 0 in the knapsack. So we can see that from the table beside on the right, all the combination or the possible combination or the binary combination representative 0101 correspond to selecting the item number 2 and item number 4, which results in the total value of 25 and the total weight of 3, satisfying the capacity requirement of the knapsack, which is the knapsack capacity. So as the result is, brute force approach determines that the best algorithm, the best combination belongs to the item number 2 and item number 4, resulting in the max value of 25. So moving on to the next algorithm approach, which is a dynamic programming. So for the general concept of the dynamic programming is to build the table from the bottom up, beginning with the minor sub-problems and progressively working the way up to the main problem. So the concept of the dynamic programming is by dividing the problem into smaller sub-problems and keeping their solution to avoid unnecessary calculations. So first thing first, dynamic programming works by creating a table to store solution to sub-problems. The next one is by filling in the table using a dynamic programming, which will be stated in the next slide. And the last one is the backtracking to find the selected items. So the next part is I want to show you how dynamic programming works exactly. So the first one is by creating a table that consists of rows and columns. So the rows representative as items, while the columns representative as a capacity. So each cell I is the rows and the J is the columns will hold the highest value that may be obtained by combining the first item I items with a knapsack represent a capacity J. So next one is determining the greatest value for each cell based on the best solutions to smaller sub-problems. So on the left side is a formula used for the dynamic programming. So by using the formula, for I equals to 1, item 1 and J equals to 0. So since equals to 0, since the knapsack capacity is 0. So moving on to the next item, which is I equals to 1, J equals to 1. Still 0, so items 1 with exceeds the knapsack capacity actually. So moving on to the I equals to 1 and J equals to 2. So consists of 12, so means that item number 1 can be included in the knapsack. So the remaining part is to fill the remaining cells for I equals to 1 in the same way, then proceed to I equals to 2, I equals to 3 and I equals to 4 in the similar manner. So still following the up, repeating the step until we find the best solution and find the best sub-problems that match with the knapsack capacity. So keep it going to the last one is the last step of the dynamic programming, which is a backtracking. So as been stated, backtracking is used to find the selected items. So regarding to the table above, starting from the bottom right corner, which is row 4 and column number 5 contains a value which is 37. We trace back through the table by following the formula which has been stated in the previous slide. By using the formula, here are the least steps of the backtracking in the dynamic programming. So firstly, we compare row 4 column number 5 with its top neighbor, which is 3 and 5 equals to 32. Since they are different, it means that item number 4 with the weight number equals to 2 and value equals to 15 was included in the knapsack to achieve the maximum value. Second, now we move to the cell above, which is column number 3, row number 3, column number 5, and compare with with its top neighbor, which is row number 2, column number 5 equals to 22. Since they are different, it means that item number 3 with the weight equals to 3 and value equals to 20 was also included in the knapsack. So moving on to continuing the same process, and we compare the row number 2, column number 5 with its top neighbor, row number 1, column number 5 equals to 12. So they are different, which means the item number 2 with the weight equals to 1 and value equals to 10 was included as well. So finally, we compare the row number 1, column number 5 with its top neighbor, which is row 0, and column is equal to 5 equals to 0. Since they are different, it means that item number 1 with the weight equals to 2 and value equals to 12 was also included. So as a conclusion is we have now backtracked all through the table and identified that item number 4 and item number 3 were included in the knapsack, leading to a maximum value of 37. Thus, the dynamic programming method finds that the optimal combination to select all the item number 4 and item number 3, resulting the maximum value of 37. So moving on to the last part, which is the explanation of why we choose the selected techniques, which is the brute force approach and the dynamic programming approach. So first one is the brute force approach. Why we choose? Because it's a simple procedure that ensures correctness, making it an excellent beginning point for figuring out the problem. Although the brute force strategy is inefficient for large instances of the problem, it can be useful for understanding the underlying notion behind the solving the knapsack problem. So the next one is the dynamic programming. Why we choose dynamic programming in solving the knapsack problem? Because it's an effective method for solving the knapsack problem, particularly for bigger instances compared to brute force, which is inefficient for the large instances, as been stated previous one. So dynamic programming also has a method that avoids unnecessary recalculations by using the table to store and reuse sub-problem answers that have been involved in the knapsack problem. So that's all from me.
So we move to the brute force running time complexity analysis. The knapsack problem is a classic optimization problem, and the brute force approach is one of the simplest ways to solve it. The brute force method involves generating all possible subset of items and calculating the total value and weight for each subset. Then, we select the subset with the highest value that does not exceed the knapsack weight capacity. Now, let's analyze the runtime complexity of the brute force approach for the knapsack problem. So, this is the runtime complexity analysis for the brute force. The first step is by generating all possible subsets. In the worst case, there are 2 to the power of n possible subsets of items, where n is the number of the items. This is because each item can either be included or excluded from the knapsack, giving us 2 choices for each item. And the second step is to calculating the total value and weight for each subset. For each subset, the algorithm needs to calculate the total value and total weight by summing up the values and weights of the selected items. This required traversing through all the items in the subset, which takes big O time. Last step is selecting the subset with the highest value. After calculating the value and weight for each subset, we need to find the subset that maximizes the value without exceeding the knapsack's capacity. This step involves comparing the value of all subsets and selecting the one with the highest value. In the worst case, this requires checking all to the power of n subset, we take O to the power of n times. And then, by combining all these steps, the total runtime complexity of the brute force approach for the knapsack problem is O to the power of n multiplied by n. As you can see, the brute force approach becomes highly inefficient as the number of items increases due to the exponential growth of the search space. Then let's move on to dynamic programming running time complexity analysis. The dynamic programming approach for the knapsack problem utilizes the concept of memoization and breaking down the problem into subproblems. By solving and storing the result of smaller subproblems, we can avoid redundant calculation and optimize the solution for the overall problem. Let's analyze the runtime complexity of the dynamic programming approach for the knapsack problem. Okay, for the first step is creating the memoization table. To apply dynamic programming, we construct a memoization table, usually a two-dimensional array with dimension n plus 1x, w plus 1. Where n is the number of items and w is the maximum capacity of the knapsack. The table will store the results of subproblems that we can reuse later. Constructing the table takes O and multiply w time. Second step is filling the memoization table. We iterate through each cell of the memoization table and calculate the maximum value that can be achieved for each subproblem. The value for each cell depends on the values of its neighboring cell and the current item's weight and value. Filling the entire table requires examining each cell once, taking O and multiply w time. The last step is backtracking to find the optimal solution. Once the memoization table is filled, we can trace back through it to determine which items were included in the optimal solution. This step requires going through the table's content to identify the items that contribute to the maximum value. Backtracking takes O and time. By combining all the steps, the total runtime complexity of the dynamic programming approach for the knapsack problem is O and multiplied by w, where n is the number of items and w is the maximum capacity of the knapsack. This is a significant improvement compared to the brute force approach, especially when n and w are relatively small.
Okay, let's talk about a comparison when it comes to brute force approach to solve the knapsack problem. When it comes to time complexity, the brute force approach generates all possible subset of items which require enumerating to the power of n subset, where n is the number of items. For each subset, it calculates the total value and weights, which takes big O of n time. Thus, the overall time complexity of the brute force approach is a big O of n times to the power of n. The exponential growth of time complexity makes this approach highly inefficient for larger problem sizes, as the number of subsets grows exponentially with the numbers of items. When it comes to space complexity, the brute force approach does not require additional data structure for memoization or tabulation. However, it uses recursion to regenerate subsets, leading to a maximum call stack depth equal to the numbers of items n. Hence, the space complexity of the brute force approach is a big O of n due to the recursion overhead. When it comes to solution optimality, the brute force approach guarantees finding the optimal solution as it evaluates all possible subsets to identify the one with the maximum value within the knapsack capacity. As we mentioned before, the exponential in time complexity makes the brute force approach impractical for larger problem size. As the number of items increase, the computation time increase exponentially, rendering this approach infeasible for sustaining problem. Thus, the brute force approach is relatively straightforward to implement, as it involves generating all subset of items without any additional data structure. However, its efficiency is hampered by the exponential time complexity, making it unsuitable for larger problem sizes. Okay, we move along to the dynamic programming when it comes to knapsack problem. Okay, the dynamic programming approach uses a table to store and reuse the result of subproblems. Filling in the table requires iterating through all items and capacities, which takes on the big O of n times w time, where this n is the number of items and w is the knapsack capacity. The times complexity is polynomial and is scaled much better than the brute force approach. The advantages of the dynamic program approach is evident for larger problem instances where it remains efficient in manageable. The dynamic program approach requires a table to store the result of subproblem, which has a dimension n plus 1 times w plus 1, where n is the number of items and w is the knapsack capacity, as I mentioned before. Therefore, the space complexity of the dynamic programming approach is BO of n times w. While it's use more memory compared to the brute force approach, this space requirement is manageable for moderately large problem sizes, and it ensures efficient reuse of subproblem solution. When it comes to dynamic programming, the dynamic programming approach also guarantees finding the optimal solution by systematically evaluating all the subproblems and reusing the optimal solution. It ensures the solution for the given knapsack problem instance. As we discussed, with dynamic programming, the polynomial time complexity of the dynamic programming approach ensures efficiency for moderately large problem size. The ability to use subproblem solutions significantly reduce computation time, making it suitable for the real-world applications, even for larger problem instances. The dynamic programming approach requires a more complex implementation due to a table creation and management, as well as understanding the concept of memoization or tabulation. However, it is polynomial time complexity ensures efficiency for moderately large problem instances, striking a better balance between optimality and computation time. To summarize, the brute force approach guarantees an optimal solution. It is efficient, rapidly deteriorates for larger problem size due to exponential time complexity and lack of reuse subproblem solutions. On the other hand, the dynamic programming approach ensures both optimality and efficiency by systematically evaluating subproblems and reusing solutions, making it the preferred approach for solving the knapsack problem in most practical scenarios. The dynamic programming approach efficiently handles moderately larger problem instances, which would be computationally infeasible for the brute force approach.
Super shy, but wait a minute while I make you mine.